This is Dr. Kristen Heck. I'm looking at tutorial problem 8.4 from Consequences of Accidents in Industries. Here it's talking about an explosion of 1 mole of amylum in a silo. What is amylum? Amylum is just starch, so like cornstarch or potato starch, a very fine powder which is also explosive, as we learned in class, so there can be some handling concerns. The maximum combustion temperature here is told to be 1000 degrees centigrade, and we should calculate the pressure rise and how much can be attributed to the temperature rise and how much to the amount of substance. What it means by the amount of substance here is we have in an explosion, the starch is being oxidized. So here we have for amylum C6H10O5. First we need to write and balance this equation in its stoichiometry. So this is a mass balance. What goes in must come out. On the left side we have 6 carbon, which means on the right side we must also have 6 carbon. On the left side we have 10 hydrogen atoms. On the right side we must also have 10 hydrogen atoms. Looking at the oxygen now, on the left side we have here 17. 5 for water, could be counted as the 5 in amylum. Here 12 in total, which means here we also need to have 6 moles of oxygen. And now we're going to solve this problem using the ideal gas law, PV equals nRT. In the ideal gas law, we can also write, if we take P and V and divide it by nRT, this is equal to 1. And so we can say that for any container, P1 times V1 divided by N1 times R times T1 is equal to P2 times V2 over N2 times R times T2. We can then, when we're comparing two systems, so here when we're comparing two systems, we can cancel out the factors from the ideal gas law that remain constant from situation 1 to situation 2. So in the first part of the problem, we're asked to determine the pressure rise as a consequence of temperature rise, which means volume inside of the silo is staying the same and the number of moles is staying the same. R is anyway a constant. So here we have P1 over T1 is equal to P2 over T2. And so I'm calling this P2, which results P2T, with the pressure that results due to temperature rise. So let's say P1 is initially 1 bar. Temperature 2 is given as 1000 Celsius. So this is in Kelvin, and for our reference temperature T1, let's take 273 Kelvin. Plugging in these values, we get that due to temperature rise alone, we would have an increase of 4.6 bar. Looking at the change in the number of moles, we can also, based on the ideal gas law, volume is the same, temperature is the same, or is anyway a constant. We can take P1 over N1 is equal to P2 over N2. And so here, rearranging for P2, the increase or the new second pressure that would occur as a result of the change of the number of moles. Let's take here, N2 is 11 moles, resulting from the reaction, the change in volume. And let's say 6 moles accounting for the oxygen, assuming that the amylum powder requires negligible space, and again using the reference pressure initially of 1 bar. We're given an answer of 1.833 bar. So now let's compare. If we have a change in both the number of moles N and in the temperature, then we can simplify R and V because volume is, the silo is staying the same size. So in this case, pressure 2 is equal to N2 here is 11 moles and N1 was 6 moles. T2 here is this 1000 degrees. Our reference temperature was 273 Kelvin, and our initial pressure was 1 bar. Here, the resulting pressure is 8.5 bar. And the interesting thing here is to notice that these factors are multiplied, so the contribution of the temperature, if we take this pressure times the contribution due to the amount of gas, the increase in the moles of gas, dividing this by the reference pressure, 1 atmosphere or 1 bar, you'll notice here that we get exactly the same value, whether we multiply these together or whether we use the ideal gas law and plug in both of those values. Do these answers match those in the tutorial handbook? No. Do we care? No, because at least we know how to set up this problem and we know how the physics behind it work.